Hi everybody, I'm Karthik from the University of Alberta. I lead a group in working on nanomaterials and devices at the University of Alberta, and the students who worked on this are mentioned. A lot of the work that's shown here is in collaboration with Professor Mojgan, Daneshmand, his group also at the University of Alberta. So today I'm going to be talking about microwave resonator sensors integrated with nanostructured semiconductor membranes for photodetection and carrier lifetime measurements. I would also like to thank the session chairs, because this talk was originally submitted to a different track who ran out of lecture sessions, and thank you for accommodating me in this session. So, uh, so titanium dioxide is a metal oxide. It's a transition metal oxide, and during the course of this conference, you've already seen a bunch of talks on tin oxide and zinc oxide, and all of these metal oxides are excellent gas sensors, and each metal oxide is more sensitive to a certain range of gases. So with titanium dioxide, it's really good for hydrogen sensing, for methane, and uh, uh, for ammonia. And as a result, it's a busy slide, I know, but I'm just trying to put a lot of information, fairly recent, that shows that this structure, which has these ordered arrays and pores, has been used for gas sensing. And my group, just a few years back, also used the same platform to construct very high sensitivity biosensors. We were able to detect picomolars of picomolar levels of human cardiac troponin, and it was not a complex sensor, but the main thing it used is because titanium dioxide is a wide bandgap semiconductor. The fluorescence background is really minimal, and it has a high surface area, which and easy conjugation protocol. So that was the main point there. Uh, Now, the other thing I would like to mention is the possibility of use of this structure, though not directly concerned to my talk in this session, in optical resonators, which you've heard quite a bit of in this session and other sessions. So you can make photonic crystals from these nanotubes by periodically modulating their diameters and creating these notches. So this is a single nanotube that's showing those notches, maybe not completely clear, and you do that by applying a programmed sequence of current or voltage pulses. But it's anodization solution-based process, so no use of photo or e-beam lithography here to construct photonic crystals, and you see the iridescence that is characteristic of a 1D photonic crystal. And more here, this was also published a while back by us in Angavante Chemi, and you see this very nice notch structure, very periodic by solution-based methods, and you see a fairly sharp stop band reflection resonance and the structural coloring. So just pointing out that this structure can also be used in optical resonators, although my talk's about microwave resonators. So microwave sensors have obviously been used for a while now, and they have these advantages that they can be miniaturized, they're compact, they're portable, they're easy to integrate with CMOS. So, uh, so, so they have those advantages, and they've been used particularly for sensing of a number of physical variables. For chemical variables, not so much, and the reason being that microwave sensors at their heart are really just permittivity sensors. They sense the changes in the local permittivity in and around in their environment, and that doesn't give you too much selectivity. So I'll talk a little bit later in this talk about how integrating nanomaterials with microwave resonators can give you that selectivity. Okay, so one of the motivations when we started out was that it's really interesting to look at the interaction of microwaves with nanomaterials. So not too much has been done there, because people assume that, you know, with light, it's obvious that nanomaterials are the same dimensions as the wavelengths of light, so or close, and it makes sense. But with microwaves, they are viewed somewhat incorrectly as being totally unrelated. But no, but you do have traps, etc., whose energies and spatial dimensions can actually correspond to microwaves. So microwaves, uh, their interactions with semiconductors, the simplified formulae looking at the real and imaginary parts of the complex permittivity and how they change. Um, and if you shine light on them, then you have a change in the conductivity, or you can also inject carriers through a gate bias. A cavity waveguide WR90, that's the common way, that's what's been used. Even in this year, you see some papers that use this method to probe the interaction of microwaves with semiconductors and nanomaterials, but those are bulky, difficult to tune, and expensive to make as well, and components to buy. So that's how we kind of started out, which is that if we could avoid the use of those cavity waveguides, waveguide resonators, and do the same thing using planar microwave resonators while keeping the same quality factors. So the quality factors of those cavity waveguides is typically about 400 to 500, and that's the same quality factor we get in this very simple ring type resonators, where you have a concentration of the electric fields in the coupling gap of the resonator, and we make our nanomaterials into a membrane and just transfer it to the coupling gap, and then you see a shift. So this is the S parameter plot that shows you a shift when the nanomaterial is integrated with the resonator, and it can be mounted or it can be even stuck to the resonator. So again, very simple to make, very simple to test. So the first application was when we were trying to study the fundamental optoelectronic properties of these nanotubes, and we wanted to understand the carrier lifetime in them. So these are, another view of these nanotubes. Notice the very ordered structure, and they can also be made on flexible substrates. So this is showing the anatase phase being present. And so after you shine, when you shine light, you see a fairly sharp change, though not very sharp, still over in the range of a few seconds. You see a change in the resonance frequency, also in the other parameters such as the quality factor and the amplitude. And then when you switch the light off, the response decays back slowly, and you can fit those decays to exponential or bi-exponential decays to extract carrier lifetimes, because you have these long-lived charge separated states in these titanium dioxide nanotubes. And it turns out that these long-lived states are due to pressing the wrong button for the laser. So the long-lived states are due to deep traps. The long-lived charge separation is due to deep traps, and we extracted lifetimes from those deep traps, and the configuration used to make the measurement is shown in this schematic diagram. But then we thought, okay, can we do this even better? Can we explore the full advantages of this setup? So we moved to active resonators, where you have a regenerative feedback circuit to reduce the losses in the microwave resonator, and that allows you to achieve extremely high quality factor. So there's a schematic of the diagram. There's an FET that's connected in a feedback loop between the input and the output port. So very quickly you can move the quality factors from a few hundred to several thousand, and in fact by optimizing it further, quality factors greater than 2 million have been achieved using this fairly simple design. And that high quality factor, for example, has been used to distinguish between solvents such as isopropanol, ethanol, methanol, water, based purely on the different changes in the very tiny changes in the permittivity, not necessarily tiny, but the changes in the permittivity of these different solvents and solutions containing them. But the high quality factor does allow you exceptional resolution, and so we tried to use it for low level light detection. So this was for ultraviolet detection. And so to give you a bit of context here, I think about a year back, the Zeong Fan group at HKUST, maybe it was 2 years back, they published this paper in Nature Photonics, where I think the best resolution they were able to get using for a UV photodetector based on single crystal zinc oxide nanowires in a normal, in a typical conduction based photodetector was I believe it was 5 to 10 nanowatt per centimeter square, and in basically a very first attempt we were able to reach 2 nanowatt per centimeter square detection limits for UV photons because the quality factor was so high. So and the way it works is interesting. We are able to, so when you have carriers incident on the titanium nanotube arrays, so obviously the conductivity increases because you have electron and hole pairs that are generated that participate in conduction now. But because there are so many traps because of the high surface area, the filling of the deep traps by light increases the number of bound charges in the dielectric and increases the capacitance. So there's both a change in the capacitance and the conductivity and microwave resonators are an excellent way to sense that. But what this and by the way, our most recent results are in the hundreds of picowatts. So we are almost 2 orders of magnitude now better than the Nature Photonics paper that I referenced. So, but what this showed us is that traps which abound in all of these nanomaterials and are generally viewed with distaste as a pestilence, right, in optoelectronic devices such as solar cells and so on, and light emitting diodes, can actually be a positive from the viewpoint of sensors, because especially when you have long-lived charge separated states and you have electrons and holes filling deep electron traps and deep hole traps. Now those trapped carriers can be made to react with species to give you that selectivity in sensing. So traps may not be all bad, and I'll get to that in a little bit. But what we try to do in this slide, what I'm showing you is, see, one of the problems is that the response time is slow, but actually it's not as slow as the plots demonstrate, because you need far fewer plots to extract the decay constant. Nevertheless, when you sensitize these nanotubes by gold nanoparticles, we are able to change the response time. So that's one thing. The other interesting thing we've observed is that when the gold nanoparticles are of the right size, you can use the plasma on resonance and also get sensitization to green light, which is 532 nanometer light. So, and we've since also worked with quantum dots and observed the ability to sensitize over a wide spectrum, over a broadband. So we are talking about broadband light detection, not just UV photo detection, tunable across the spectrum, and yet preserving very low levels of detection. So coming back to the issue of selectivity and traps, so this was work we published, and I urge you to look it up if you're interested in this, earlier this year in nanoscale. So where we showed that because of the interaction of trapped states with different solvents in a unique manner, that our sensors, the microwave sensors, resonators integrated with these nanotubes, were able to distinguish between isopropanol, ethanol, and methanol. So they had distinctive signatures based on their decay constants. And the reason this is happening is methanol and ethanol and isopropanol, they're all hole scavengers. So when you have resonators and when you also shine light and this allow it to decay, so the holes are now scavenged by these alcohols, but each in a slightly different manner, and the resonator is able to pick up on that. So this is a triumph, because the molecular structures of all these alcohols are so close that even ligand affinity binding based methods are not very effective at picking up the differences between them, because their physical and chemical properties are so close. So but the microwave resonators, through the trap interactions, are able to pick up on that. So with that, I come to the conclusions, which is that self-organized titanium nanotube arrays are versatile platforms for optical cells, which I haven't shown, and microwave sensing of analytes such as biomolecules, volatile organic compounds, alkali ions, and light levels. Titanium nanotubes can be used to construct one-dimensional photonic crystals through a low-cost, high-throughput bottom-up nanofabrication process. The sensing functionality can be vastly extended. You can get sub-nanowatt UV intensity detections, and you can also detect molecular monolayers. And the interaction with surface trap states and electron hole scavenging action can be used to imbue these resonators with selectivity. And the use of sensitizers such as gold nanoparticles and quantum dots offer a route forward for tunable broadband light detection and also control of response times. Thank you.